Good morning, reInvent. Welcome to Friday morning. Hope you got some sleep last night. My name is Micah Hausler. I'm a senior system development engineer at Amazon Web Services. I work on the EKS team.
My name is Dean Delamont. I work in global cloud services at HSBC, where as a leading financial institution, security is foremost important to us in everything we do in the cloud. I'm grateful to be here with Mika today to talk to you about some of the security controls available to you to secure your Kubernetes clusters, and to share with you some of our learnings at HSBC from utilizing Amazon EKS. Just as a bit of background information, at HSBC, we recently embarked on the use of Amazon EKS. Our primary use cases were single-tenanted clusters and multi-tenanted clusters. Prior to that, I worked on design and development of multi-tenanted clusters for Kubernetes on private cloud and public cloud.
So today we're going to be talking about running high security workloads on Amazon EKS. The agenda for today, we're going to have a little bit of background, so setting the stage for what we want to talk about, how we think about securing systems. We'll talk through an example scenario of something that could happen to possibly your organization, some other organization with Kubernetes, some mitigating controls that you can put in place to prevent and secure your clusters from attack. Then we'll have a final summary. We'll do a Q&A afterwards out in the hallway, so please come see us afterwards. We'll skip the related breakouts because those are mostly complete. So before we dive into details about running high security workloads on EKS, we want to set the tone for the presentation. So we want to talk about the ways in which we approach and think about securing systems. I don't want to scare you, but security is hard. It requires you, the defender, to get it right every time. The attacker, your adversary, has to get it right just once. So again, it's asymmetric by nature, but it's possible to do and do with good practices. So we're going to talk through some of that today. One of the first models that I kind of want to present you with is the CIAA model. It's an acronym for these four things. Confidentiality. This refers to authorized access to information. So the right person accessing the right information and not necessarily revealing that information access to others. The second pillar being integrity. So this is authorized modification of information. So this is updates, writes, deletes, and only the right actors in your system doing this. You don't want someone deleting a record from a database that they shouldn't. Similarly, you wouldn't want someone updating an address or something that they shouldn't. And availability, so this just refers to information being accessible when it's desired. So you've probably heard of DDoS or distributed denial of service or just denial of service attacks. This is an attack on availability. This is pretty critical to most applications. And then the final pillar being accountability and auditability. So this just refers to the tracking of access to information or modification. So you'll see around this area, you'll see things like audit logs or just records of access. This is what you use to help replay what happened when. It might be forensic in the case of intrusion, or it could just be a regular review and audit of systems.
Okay, so we're going to talk about shared responsibility model. So no better place to start. So one of the important distinctions to make when using Amazon EKS is obviously Amazon is responsible for the control plane, but you as the customer are responsible for the data plane. That entails the EC2 instances, so your worker nodes where your pods and your containers reside. So with that, you have a set of responsibilities that comes. So essentially everything shown on the line above in the simple picture there. So here you're responsible for Kubernetes-related configurations, so things like RBAC, so defining RBAC in a least privileged way. So you've got cluster roles, general application roles, you've got separation of roles and responsibility, so you're defining RBAC permissions, RBAC bindings, etc. In addition, you're responsible for your Kubernetes configuration in terms of your security posture. So things like Kubernetes pod security policies, which we'll talk about later what that is and how you can use those. So those are the things that define the rules how your pods can run. You're also responsible for defining things like Kubernetes security context for your pods and your containers, as well as defining things like Kubernetes networking policies in terms of your cluster egress, ingress. So in addition to that, just like any ordinary Amazon service that you would use, you're responsible for the configuration of the VPCs, so things like your security group rules, again, in a fine-grained way. In addition, you're responsible for defining things like your endpoint policies and your endpoint definitions, so private link, for example, on the API server for kubectl access. So in addition to that, though, you're, like generally, if it's an EC2 instance, you're responsible for the hardening of the OS. Here, it's the same situation. So with that, there it comes additional responsibility because you're using shared host here. You have many pods running with containers in them on a single host. So essentially, you're responsible for ensuring that when you harden that host, you're doing so that things are isolated. So you've isolated containers from one another, you've isolated containers from the container runtime, you've isolated the Kubernetes processes from your containers, and you've isolated the underlying host OS. So we'll go through what that all means as part of this talk later, and we'll talk about some of the controls available to you to be able to do that. So just to note, if you're offering Amazon EKS cluster back to your teams within your company, where you've got a single cluster, lots of applications, you're essentially providing a shared cluster as a multi-tenanted cluster. And with that, it's even more important to ensure that you've got these controls of isolation in place. And again, we'll go through all those types of controls and what's available to you as part of this talk.
One of the other models that we will talk about today is the actors and capabilities model. So this just is a high-level concept of actors being the nouns in the situation. So this could be anything from application developers on a cluster who have access to a cluster. This could be a cluster administrator or an AWS administrator. This could be an application process on a Linux box or a Windows box even. It could even be an anonymous user of your system operating over, accessing your website. And then the capabilities are the verb side. So this is things that the nouns can do. This could be credentialed access. This could be network access. This could be things like system permissions, Linux syscalls, that kind of thing. It could even be the ability to time responses. These can get really tricky when you get into like the sort of the cryptographic space. The thing that you want to start asking yourself when you're thinking in this mode is, how can I try to minimize what verbs the nouns can do? So this isn't an exhaustive list. This is meant to get you thinking. And some of these are really hard to think of, but this is, as you start thinking about these things, this begins to form the basis of your threat model. So let's apply this a little bit here. So in this example situation, we have an Amazon EKS cluster that's managed. That's the managed control plane that AWS offers. We have the VPC, that's the customer VPC, that might be your VPC. You have EC2 instances in there that could be EC2 or AWS managed nodes, EKS managed nodes. And you also have subnets and security groups in this VPC. Again, more actors here are, you have pods running in your VPC. These are processes running on servers. You have application developers. They have network and credentialed access to the Kubernetes cluster. You have cluster administrators who have network and credentialed access, but different levels of credentialed access to the Kubernetes cluster. But their network access, in this case, is over AWS Direct Connect. And then you might have an external attacker or adversary, and they might have a different level of network access that's not credentialed over a load balancer, so it's restricted to specific ports, specific protocols, that sort of thing. So as you look at your own application, you begin to, when you draw a diagram like this, you'll begin to see the access patterns, and you can start to enumerate, okay, who can do what, how can we minimize that to only what they need, and that begins, again, to form the basis of your threat model.
Okay, so we're going to talk about basically threat models and attack vectors. So the following simple diagram illustrates some of the attack vectors that you may face in terms of your Kubernetes clusters. So talking about that, attack one, HTTP request, malicious script request. It's pretty difficult to identify an attack like this, let alone prevent it. Think of this. What if you deploy, say, an application such as Apache Struts that may have, say, a vulnerability in it? A malicious agent could get control and exploit the control systems of your Kubernetes cluster. So again, pretty difficult to identify these types of attacks, let alone prevent them. Okay, so think of this. What if an attacker does get hold of a container? So now the attacker's got hold of the container. What can he do? Could they escalate to root on the host OS? Could the attacker abuse the Kubernetes system resources? Could the attacker access the namespace and resources of another application, such as their secrets or their data? Could the attacker exfiltrate data? So this is by no means an exhaustive list, but we're starting to construct, as you can see, a very simple threat model. To the point, you can't account for every single attack vector or vulnerabilities, but you can, through a multi-layered security approach and through good configuration, isolate your containers and reduce the attack surface and reduce your exposure to such attacks. And we'll talk about all of the controls that we're going to go through, which will help you do that as part of this talk.
So before we dive into the controls, I want to just talk through sort of an example scenario here to kind of frame what we've talked about and give you a real-life possibly example here. So a developer in your organization has access to Kubernetes. Say you're a cluster administrator, and you've given credentialed access to your developers. And so a developer in your organization finds this blog post that says, promises to automatically, magically configure your Kubernetes cluster and give you insight, observability, security, safety, whatever it is. And all you have to do is apply this simple add-on in Kubernetes. So they run on their command line kubectl apply, and they reference this blog post that they read, and then what happens? You have now a cluster role binding, service account, and a deployment. And this deployment is going to solve all your problems. And then a week later, you're reading that same news site, and you find another post that talks about malware being distributed via Kubernetes application YAML. And it just so happened that it was the same blog post that your developer read. So what happened here? Stepping back again to our sort of actors capabilities model, we have an application developer who had network credential access to Kubernetes, and they created a deployment as well as a few other resources in the Kubernetes API. The Kubernetes API then created a pod. The deployment creates a replica set creates a pod gets scheduled onto a node starts running the container. And now this malware pod has system access to your application. It has network access to possibly your Amazon RDS database in a different subnet. It has access to your Amazon Elasticache, whether that's Redis or Memcache or whatever you're using. And it also has egress internet access. So this is just, again, kind of a spooky example, but something that could possibly happen, right? Something very seemingly simple and innocuous had big consequences. So how can we prevent something like this from happening? You as possibly a cluster administrator, someone who's responsible for interacting with the Kubernetes cluster. We want to talk about controls, and as we talk about those, we'll break it up into three logical sections. So we'll talk about the Kubernetes API, things you can do in just Kubernetes to prevent and help yourself prevent from an attack like this. Things in the container runtime and operating system level, and then also controls in the AWS side, features and services that AWS provides to help you when something does go wrong and to prevent something from going wrong. So the first section that we'll talk about, Kubernetes controls. So some of these are something you might not think is a security control, but can actually be really helpful. So the first just is being namespaces. So this is a logical partition within your Kubernetes cluster. This is the reason why I list this in under a security control is in the Kubernetes authorization system, you can actually give users specific access to only a namespace. So if you have more privileged or different levels of access or something in a different namespace, users can only see applications in their namespace. Service accounts, these are Kubernetes identities that are assigned to pods. So this could be an identity that the pod uses to talk back to the Kubernetes API server to get information. It could be some kind of controller thing, like an application load balancer, ALB ingress controller, or it could be used for getting external credentials. So we'll talk about later, the IAM for service accounts feature. But service accounts are a way to give your pods an identity, whether it's in the Kubernetes system or in external systems. Resource quotas. So this is a great Kubernetes tool to limit how many resources you can have in a namespace. Say you have a namespace that you want you don't want it to have any load balancer services, so you don't want any external access to this possibly ever happening. You can set the number of load balancer services to 0. Same for a number of pods, volumes. Almost any Kubernetes resource, you can restrict how many can be created in this certain namespace. So it's a great tool if you want to start locking down namespaces. Another is network policy. So this is a pod-aware network control that's implemented by different backends. And if you're using Amazon EKS and our CNI container networking interface, you can also apply Calico network policy to enforce this. Think of it sort of similar to AWS security groups, but it's at an IP tables level. And it's, again, enforced by Calico in EKS by default, or if you add it on. Limit ranges is one other resource you can use. So this basically limits how large of a pod container or volume can be. So if you if you have some deployment being created that you didn't necessarily want created, that might request 32 gigabytes of memory on it, and you have a large box and you don't want it using that much, you can restrict how large pods, containers, volumes can be. Some other Kubernetes controls are, here we go, role-based access control. So this is the authorization policy API. So this allows you to restrict which either service accounts or other external users in AWS can access which resources in Kubernetes. Think of it sort of similar to the whole IAM policies in AWS. This is the sort of Kubernetes implementation of access control within the context of the Kubernetes cluster. Another great feature is dynamic admission webhooks. So this allows you to basically, as requests are created, either modify them on the fly or just stop or allow them. So this comes in later. We'll talk about the open policy agent. But you can write your own webhook to say, I only want resource with this policy attached to it. You can do this with dynamic admission webhooks. Another is the API audit log. So in EKS, you can actually, we'll talk about this a little bit more later, but this gives full API logging on every action against the API server in a structured JSON format. And it can even include request and response bodies. And then the final one is just the pod security policy. So this is restrictions that you can put on pods and containers in terms of what they're allowed to do.
Okay. All right. So pod security policies. Thanks. So what is a pod security policy? So pod security policy, is the best way to think about it, is a means to inject rules on the conditions in which a pod can run on your cluster. And so these are cluster-wide resources. They're things you authorize the pod to use, and you define a set of rules in terms of the conditions in which it can run on the host. So for example, you could put must run as non-root, must not use host network resources, must use only whitelisted volumes. So there are many controls you can specify in terms of the rules and conditions in which a pod may run or not. It's enforced via a mission controller. So if those rules aren't satisfied when that pod tries to deploy, so say, for example, you've written in the pod definition for your manifest and deployment, you've written host network equals true, and in the pod security policy, you specified false as not being allowed, then it will deny it from running. So essentially, it's a means, as a guardrail, if you like, to prevent pods running in a highly privileged way. And it's something which is very useful when we think about isolation of pods and containers from the host. So this is where you can start to define some of the rules around that isolation. So the means of doing this as well gives you other rules as well, which you can specify. So for example, within pod security policies, you can also specify your Linux-related security controls, and we're going to talk more later about that in detail. But you can specify, for example, Linux capabilities in terms of the general capabilities that the pod is allowed to have in utilizing the host resources, because again, shared resource in terms of the host OS, many pods all consuming that same resource. You can also specify things like allowed system calls or denied system calls by specifying profiles within your PSPs. And again, we're going to cover this in detail. So when we think about that, one way to consider it is if we illustrate it, and this simple diagram illustrates this. So here we have a cluster user, and the cluster user is attempting to do a pod deployment using kubectl. So they're making the action against the API server. So you can see they've got their pod definition. The admission controller and the Kubernetes API server essentially are interacting with, if you like, your pod security policy in checking the configuration that's allowed within that pod security policy. So this particular pod that they're deploying has been authorized to use the pod security policy here. And based on that condition, the pod, if it meets the conditions in the pod security policy, is allowed to be deployed. So that was a very simple kind of high overview of it. Here's an example of a restrictive pod security policy. This is a simplified one, just to illustrate some of the controls available to you when using pod security policies. So here we've got privileged equals false, where we're preventing essentially the container from escalating to root, which is an important one because you want to prevent container breakouts onto your host, where a container may then perform some of the attack vectors we spoke about earlier, such as data exfiltration. Here, we're restricting the pod to specific volumes in the container. So we've defined these are the allowed volumes that that container can access. So we're not allowing it to have all host access in terms of the volumes on the host. And here, by setting host network equals false, we're disallowing the direct use of the host network, which is important to isolate the container from the host networking resources. So using container port rather than host port, for example. And here we're preventing the writing to the root file system. So again, equally important, if a container has been exploited by an attacker and they've got hold of the container, the last thing you want them to do is to have the ability to write to a root file system on the host, because it has many permutations and risks associated with it. So we're going to give a very short pod security policy. The purpose of this, demo on the pod security policy. The purpose of this really is simply to illustrate pod security policies and how they're enforced via mission controller. So in this simple example, we've got a couple of actors, which I'm going to show you. We've got basically a cluster administrator that's created the pod security policy. Oh, hang on. What happened there?
Red.
No. Strange. Sorry, bear with us a second. Should have played. No?
Let me do it really quick.
Sorry, bear with us a second. It's, there we go. Okay. Apologies for that. Okay, so we've got a couple of actors. We've got cluster administrator, we've got application developer. Cluster administrator has created a PSP. The pod has been approved in this case to use the pod security policy, which is associated with. When we get to the point, so you can see here, is our restrictive PSP that we've created. So like the example we showed earlier. And we're just showing here, yes, you're authorized to use it. So we're demonstrating the pod's been authorized to use that pod security policy. And now we're going to run up the pod. So in this case, actually, it's BusyBox, sorry, not NGINX. I've got a demo of NGINX in a second. So in the first instance, it's not violating the pod security policy, so it's allowed. The second instance, we see denied. And that's because you can see we specified in the pod specification host network equals true. So this is just a very simple demo, literally just to illustrate the power and capability of pod security policies to help isolate pods and containers from hosts. You can define many rules and many conditions, and I do recommend you look at that in your own time and try to see how you can implement rules that will isolate better your containers. So another control within Kubernetes is security contexts. So there are various forms of security contexts. There's two, in fact. There's pod security contexts, there's container security contexts. The bit you need to be mindful of with this is cluster administrators. You should be in control of creating these. It shouldn't be a situation where you've got, say, a cluster administrator creating pod security contexts and application developers creating container security contexts. Because if you do that, the container security context will override the pod security policy context, which will mean that one could escalate their privileges. So security contexts are slightly different from pod security policies in that pod security policies are cluster-wide resources like we spoke about. They're essentially guardrails which set the conditions in which you can deploy. This is really a means in terms of security context to inject your variables. So think of it as a means to set environmental variables. So here I'm defining the labels which my essentially pod or container will utilize. Here I'm defining the absolute conditions in which that pod and container will itself run. That may be a subset of what the pod security policy allows, for example. So this is an example, security context, just a very simple one. Similarly, you can put rules in the security context for your specific pod and container. So in this example, it's a pod security context, where you can see here we've got, again, prevents root escalation, where we've got root escalation equals false. Here we've defined a UID, which is 1,000. Why we've done that is to stop the container from running essentially as root. So that, again, that was a very, very simple example. So we're now going to move down the stack. So we've been talking about Kubernetes security-related controls. We're now going to talk about container runtime controls and operating system controls, so going a bit deeper. And we're going to talk about that in the context of the attack vectors we were speaking about earlier in terms of how you can mitigate against some of those attacks. So one of the controls available to you when you talk about Linux-related security controls is called SELinux. So what is SELinux? So SELinux is a form of mandatory access control. It's derived from Unix and Linux early days of discretionary access control. So traditionally, you're all familiar with doing sudo root and getting root privileges when needing to, when you're on a particular Linux host OS. In mandatory access control, it's subtly different in terms of that it's not based on the same controls that Unix traditionally had and Linux. It's a derivative from that where they enhanced it based on essentially having a label and a type, where essentially regardless of whether you've managed to, say, get semi-root privileges, you're not allowed to perform functions if they're outside of your label and outside of your type. And we're going to go into detail on that, so if bear with us and it will become clearer. So here, the enforcement of SELinux in terms of what a pod and container can do outside of Kubernetes on the host itself is enforced by the use of labeling that applies to files and processes and ports. So typically the kernel will basically label the process itself. With containers, we have specific ways in which we do that, and we'll talk about that in a second. In terms of files, they're usually extended attributes as part of the file system, and they're generally inherited from the parent directory. So when working with SELinux, there are a couple of modes in which you can run SELinux. So there's a targeted policy in SELinux, which basically protects the host processes, so your general Linux processes on your host, so part of your Amazon Linux processes, essentially. The other modes you have are things like unconfined. Don't recommend it, but it's to be aware. Unconfined in SELinux has a specific module that basically means what it describes. If you run something as unconfined, SELinux will ignore it and will allow it to do whatever it wants to do. So there's a security threat and a risk if you run processes as unconfined. So generally only do that when you're extremely confident in the process itself and that it doesn't represent a security risk to you. I would generally advise don't do that though. The other is multi-level security and multi-category security. Don't worry too much about the detail. SELinux has kind of two modes in this. One is a very simple one, which you set basically a level, and we're going to show you an example of that in a minute. There are more advanced use cases of SELinux, which I don't recommend because they get very complex. But if you simply set labels and types, that will get your enforcement working, and it will get you having isolation at the level of the host OS between the containers and your host, as well as containers from one another. So labeling can comprise of 4 parts. Again, it's only type and level, which are the ones which are enforced on. So the others are really optional as to whether you use them. So you might be wondering, what does this all mean? What's this guy talking about? So SELinux, put very simply, why would you use SELinux? So SELinux basically protects the user-land software. So think about container user space on a host OS. So every container is essentially running in a sandbox in its own user space. So it's protecting that user space and preventing another container from accessing the data on that particular user space or abusing it. It also protects you against bugs. So we had quite recently, there was a runC vulnerability where an attacker was able to escalate through runC to go through IPC calls to get to root escalation on a host, and then they were able to attack the host. So SELinux in this particular example stopped that attack. There are many other examples like that, which are Kubernetes vulnerabilities, essentially, which things like SELinux can protect you against. So Kubernetes is vast in terms of its capability, and it's also vast in terms of its code. And there are vulnerabilities. They do turn up. So this is one of the things you need to consider and think about: is how am I going to protect myself against those types of things? And SELinux will give you that. The other is misconfiguration. So if you've got bad configuration in Kubernetes, where things aren't isolated using namespaces and service accounts in a well-defined way, then SELinux is your last line of defense that will protect you against that type of thing. So if you're running SELinux, that will prevent that kind of scenario. So the simple diagram here illustrates this, where we've got basically 2 pods and containers running up. One's labeled container_A_T, the other's labeled container_B_T. So unique type. in both cases. And then they've got a file which is labeled, as you can see, SO, and the other one's got SO. Don't worry about the detail, just know that it's unique. And it's that uniqueness that causes the separation. So container underscore A underscore T can access its files, can access its data, but it can't access the data of container underscore B underscore T. Be aware, if you run, for example, container B underscore T as unconfined, then it will be able to access container underscore A's files and everyone else's and everything else. So don't do that generally. So another way of thinking about SELinux when we're looking at this is think of it as in your last line of defense. So this is really what isolates your containers at the level of the Linux host OS from one another. As even if container B underscore T gains semi-root privileges or root privileges, then as long as you've got unique labels set and you've got SELinux set to enforcement mode, essentially that will prevent that container from accessing another container's files and data, which prevents the number of attacks we spoke about earlier. So SELinux has a specific module, just to be aware, which is called container underscore T, which is a general module for containers. You would deploy that together with your Amazon Linux AMI2 image as part of your package deployment, and you can deploy a number of packages that come along with that. When you run SELinux, essentially the way that the enforcement works is it's based on essentially a policy. So with the module that I described, which is the container underscore T, that essentially defines what it's allowed to do effectively. And you can set, for example, your own, effectively, policies and profiles for containers. So it's not one size fits all. So similar to when using, say, pod security policies or security contexts, you wouldn't have one for everything. You would define different ones based on the functionality required by each of the container and the pod. And here, for example, you would have, say, non-privileged containers, so general workloads for your applications, which you would have a restrictive set of SELinux controls over, just the same as the restrictive PSP. And for things that require, say, more privileged access, you would give them permissions. So if you're running, for example, FluentD, with Amazon EKS, you would create a specific profile for FluentD, allowing it to access a var log on the host system. So that's just an example. So the SELinux has a lot of flexibility in its use, and it's important to note that, because when you're dealing with containers, it's not just your applications. You've got system containers as well, which you need to consider, like kubeproxy, core DNS, etc. So applying SELinux to containers. So the good news is it's not that complex. So you've got Docker, for example, and Docker has, in Docker config, the ability to set SELinux enabled. And what that will do is it will automatically label your general workloads and your applications as a container underscore T as a type, and it will also give it a unique MCS level. So without you having to do anything, every time you run kubectl deploy, it will automatically create a label and assign it to that container, isolating it from one another. So your applications are then isolated at that point, which protects you against those security threats. Another way, say, for example, you've got, like we gave the FluentD example, and you need to give it more privileged access. Another way of doing this is to set your own profile, essentially, in SELinux and give permissions for it to access varlog. And you would do that using things like security context with Linux options, where you can define the level. So one point to note is in pod security policies, you don't define, remember, like I said, pod security policies are guardrails. They're not kind of context stuff with your kind of variables for how it's your environmental variables for your pod in terms of defining its definition. And so in a security context, for example, you would define level and type. Here I've given level, just an example. In the pod security policy, you would specify something that must run as. So it's a guardrail to say it must have security context, in effect, with SELinux on options. So I'm going to give a very short demo for SELinux. The purpose of this is just to illustrate SELinux in enforcement mode. And here we've got nginx as a container, which I'm running up. And I'm intentionally running it up to violate, essentially, my SELinux labeling by trying to get it to access a file on etc. on the host.
I'll play it here.
Yeah. So for the purpose of this demo, I'm running this directly from Docker rather than kubectl to keep it short. And so here, what I've done is I've created a file called myfile.txt. Well, it's just a myfile.txt file. I'm running up an nginx container instance. And what you'll see is the first time that the nginx instance runs, you'll see that it is able to read the file. But then, basically, when it attempts to write to the file, so I do an echo at some point. So at the moment, I'm executing into the Docker instance here, so I'm SSHing into it. And then I attempt to do an echo against the file. So it's just showing I can actually read the file. So reading the file is fine. Now I'm echoing to the file, and we get denied. And that's SELinux stopping me basically doing that. So I'm exiting now and going back onto the host. And SELinux has a set of logs in var log, which contains basically the exception, which if SELinux is denied an access, it will give you the exception. And here you can see it's got the append denied, and it's telling us why it's not allowed it to access that particular file. And that's because of the labeling essentially doesn't consist, or it's not consistent with that of the container, and we haven't allowed it to do so. So, again, simple demonstration, but it does illustrate the power of SELinux. So some practical tips for SELinux. So if you're running, like the example of FluentD, or you're running other, say, plugins for Kubernetes, then typically you would want to create a policy that allows it to perform the functions it needs. So here, we would create a policy that would allow it to access var log. You would do the same with other Kubernetes system containers, for example. SELinux, again, like I said, if you try to run things unconfined, which is an option, so if you're not confident in creating the policies, and say, for example, you trust kubelet, you might run it unconfined. And kubelet's not the container here, by the way. SELinux applies to processes, like I said earlier, and so you would run SELinux against kubelet as well and label it. But you have options as to how you do that, so you could run it unconfined. So the good news is that you have a log entry, and with that log entry, you can automate your creation of your policies and your security. So you can use, there are various tools like SEAlert that gives you a clear message in terms of the exception itself that's clearer than the one I gave you. And with that, it gives you the actual command to fix the issue. So it will tell you, hey, do you want it to access this? If you do, run this command. And so it's very simple as a cluster administrator then to run the command if they want to give it that privileged access. And what that does is updates the policy essentially in the profile for the module for that particular container behind the scenes. You can also do things like, say, for example, if you're running in a development environment, you've got lots of containers, and you're unclear what functionality are needed by those containers. You can run things like audit to allow, or write your own scripts off the back of audit to log, and that will generate for you a policy, which then in your production environment, you can set to enforcing mode of SELinux, and then run that in the least privileged way. So that's the kind of method of doing dynamic profiling yourself. There are a couple of command lines, restorecon, chcon. So these are for if you've got a labeling issue. You shouldn't generally get labeling issues, but say, for example, you do with a file and your container can't access its file, then you can use these commands to actually change and modify essentially the labeling. Okay, so still talking about SELinux, sorry, Linux-related security. There is another available tool to you, which is called seccomp. So subtly different. So SELinux, like we said, mandatory access control based on enforcement of type and label. Seccomp is different in that it's not going to isolate your containers from one another or the host like SELinux was doing. But what it will do is will protect essentially the kernel from bad syscalls. So seccomp essentially is a module that intercepts kernel calls and will basically only allow whitelisted syscalls that are deemed safe calls. So this is where a container might subvert out and try and make a syscall where it can gain privileges. So the type of thing you want to kind of obviously prevent against. So with seccomp, there are a couple of ways which you can use it. Again, you've got unconfined, don't recommend. There is a runtime default configuration you can use with seccomp. Docker also has a default profile you can use with seccomp. The Docker one is quite good. It has around 312 allowed whitelisted syscalls, which are deemed safe syscalls. And should, for example, any new kernel-related syscalls get developed, they will be blocked automatically. So seccomp is a very powerful tool to kind of protect your host. Remember, shared host. So you want to ensure that that's protected from containers when you've got a rogue container and attacker's got hold of it. So alternatively, you can create your own custom policies as well with seccomp. So you can create your own profiles. In this case, seccomps are profiles, not policies. We call them policies purely because they're setting security context. We'd recommend generally, like I mentioned before, it shouldn't be one size fits all with things like pod security policies and security contexts and even SELinux. So with SecComp, the recommendation would be have a general profile for your general application workloads, but create essentially profiles for the things that require privileges. So where you've got something that does require additional syscalls because it's a privileged container, then give it permission in a kind of fine-grained access way, and then you're doing that in a well-described way. Okay, so I think we've actually covered that, so I'm probably not going to cover that because we've kind of said that already. Might I go back? Hang on, sorry, bear with a second. Okay, so moving on. Container image management. So slightly different topic, but equally important to everything we've just discussed earlier. So whilst I've talked about attack vectors protecting and isolating containers and everything else, one other attack vector is the image itself. So one could basically put a rogue image into the cluster. And so you have a number of attack vectors you face here. So here we've got external attacker could use the image registry credentials, call the container runtime API publicly, and do Docker pull and Docker run. We have internal attacker could export image registry and push and pull images externally. We have access to container runtime directly, so they're spawning a container directly on the host OS, bypassing Kubernetes and all the controls that you've spent a lot of time and effort building. You could pull a rogue image into the cluster that has malware on it, for example, and that could result in a security incident. You could push images outside of the cluster, potentially if you've stolen, say, the credentials. You could potentially pull an image, then push it out, and do a data exfiltration. Another attack vector is man-in-the-middle attack on your CI/CD pipeline. So perhaps you have a CI/CD pipeline because you're doing things in a well-defined security way, and you're scanning images, and you're only using scanned images for your clusters, which don't have vulnerabilities. An attacker might essentially attack that by stealing the Docker credentials and then put an image in themselves which hasn't been scanned, thereby bypassing everything that you've done there. So these are just some of the attack vectors that you could face. The first one in the example of essentially accessing Docker API publicly, you would have to have gone out your way probably to allow that to happen, because generally the Docker API shouldn't be exposed publicly because you should have defined your VPC so it's all private. But we'll talk about some controls around that. So these are just some of the controls available to you. So Amazon ECR recently announced ECR endpoint policies. With that came the capability of putting principal org ID as a condition in your policy. That's useful because it would prevent basically the pushing and pulling of images outside of your cluster by an IAM entity that's not part of your organization. So it's a very good control there that I would recommend you use. Another thing is called Open Policy Agent, which we're introducing here. So Open Policy Agent is relatively new in Kubernetes. It's a form of control using a mission controller to enforce essentially preventative incidents from occurring. So, for example, you can write an OPA policy that will whitelist registries in terms of image registry, and it will intercept essentially calls to the container by the container runtime to kubelet. So where we've got kubelet and container runtime interacting together, making calls to pull an image from your Amazon ECR or from an external entity that's not your Amazon ECR, it'll intercept it, and it will prevent it from accessing a whitelisted registry, a registry that's not your whitelisted registry. So quite a powerful tool there, and that will stop some of the attacks we spoke about earlier. You've also got the ability to use OPA to enforce signing of images. So you can put a condition, must use only signed images, where you can put, and I'll show you an example of an OPA policy in a second, but you can put a condition on that to stop an attacker basically stealing the credentials and pushing an image into your cluster with malware on it, because only signed images essentially will be allowed. With the container runtime API being accessed externally, you can stop that by simply doing things like using Unix sockets rather than a general configuration. Obviously, configuring your VPCs and your security group rules to ensure that it's not publicly accessible would be another control. So here is a very simple OPA policy. In this policy, we're basically preventing the use of any images other than those that have been scanned and are inside our Amazon ECR registry. So you can't bypass that at the point of deploy with a pod. It's forced to use images only from that. So if you define something different in your pod definition and you attempt to pull, it will be rejected essentially by a mission controller. We could here have the signature, so we could put a condition on the SHA-256 signature to say that only a signed image is allowed, and that will force basically the signing of an image, and it will reject basically the pod from being deployed as in the same way, effectively. So just to mention, at HSBC, we've got these types of policies. We've also got additional policies around lifecycle management. So as well as scanning images, we basically maintain state. So should a vulnerability appear in an image, we will ensure that that image is not running live, and we enforce basically pods to go over to new images. So over to Mika.
Yeah. So the last section that we want to talk about is AWS controls. So what are the features and services that AWS provides you to help you secure your workloads running? So some of the first ones that I want to talk about are more EKS specific. So control plane logging. We talked about earlier, API audit log in Kubernetes. So in EKS, when you create a cluster or after creation, you can enable log uploads to your CloudWatch logs. So the logs that we offer are the API server, just normal API server process logs, the controller manager in Kubernetes, the scheduler, the authenticator, and also the API audit logs. And these, like we said earlier, these API audit logs are well-formatted, structured JSON that even include request, response, which user requested it, IP address information, that sort of thing. One of the things I really like doing, whether it's for a security issue or just general debugging, is using CloudWatch Log Insights on this. You can actually query very quickly which user had 400s, or why does this user have a 400? If you're trying to debug an RBAC policy or something, it's a great way to look into sort of what's going on in the cluster. Another feature EKS offers is endpoint access. So by default, when you create an EKS cluster, the endpoint is public. It's on the internet. If you don't want that enabled, you can turn it off and just have the Kubernetes API server be available in the VPC of your workers. Another feature that we offer, access control, and authentication control. So when you talk to a Kubernetes cluster as a user, you're using your AWS IAM identity. So we basically give you the ability to say which AWS IAM users can access the EKS cluster. Another feature that Amazon ECR, the Elastic Container Registry, provides is, this is recently launched, image scanning. So as an image gets pushed, it can be scanned, and you can get notified about CVEs in the base OS of your container images. And then one other feature that EKS provides is the IAM roles for service accounts. So this allows you to assign IAM roles to specific pods. So we'll talk about that a little bit more. Why would you use this? So there's a number of reasons that we really feel excited about offering this to our customers. One is just that we feel that it's secure. So you, as a customer, when you use this feature, you can set IAM policy restrictions on the IAM roles around which Kubernetes service account can assume that role. So you can say this namespace can assume this role, or this just one individual service account can. And then it also enables you to isolate AWS permissions to your pods. So if you haven't been using this, you've been using, say, the EC2 instance profile for all the pods on an EC2 instance, you have like a shared credential across different services. So maybe one service needs Dynamo, one needs S3. You have to put both on the same policy. And so a pod that maybe only needs S3 access now has also Dynamo access that you would like to limit. So this feature lets you do that. Credentials are also automatically rotated. The service account token that gets mounted inside the pod gets automatically rotated, and then the AWS credentials that the pod fetches are automatically expired and updated by the SDK. And then this is just a really nice feature for EKS. You can actually run this IAM roles for service accounts on your own managed Kubernetes if you want. We built it as a generic feature that could be run elsewhere, but for EKS, one of the other features we provide is we automatically rotate the signing key that backs the service account tokens. So you don't even have to think about it, you don't even notice it, but we do that for you. And then it's also a really easy integration. So all you have to do as a user is create an IAM identity provider for this cluster. And our documentation will walk you through the setup for that. It's fairly easy. And then once that's all set up, you just need to update your roles policy and then annotate the service account in Kubernetes and say, for pods that are using the service account, here's the role that I want it to use. And we'll do a demo in a second. This is built into the AWS SDKs and the CLI, so we'll see how this works. The other thing that we really like about this is it's auditable. So when you have pods that make AWS calls, you can actually go into CloudTrail, and look at your CloudTrail logs to see which service account made the API calls inside the cluster. So we'll go through the demo really quick here. So in this demo, the first thing we'll do is we'll actually demonstrate not using IAM roles for service accounts. So what we're doing is we're creating a service account in the Kubernetes API using kubectl, the command line client. We're going to display that service account YAML definition. So you can see it has a secret associated with it that was automatically created by Kubernetes. We're going to run a pod in the cluster that uses the service account. All this pod is doing is running a sleep. So we're getting the pod name from the Kubernetes API server, and then we are going to display the volumes that are attached to it. So when you specify a service account for a pod, the Kubernetes API server automatically creates a volume on the pod and attaches the service account token to the pod. So as we shell into the pod, kubectl exec, and run the AWS STS get caller identity call, you can see we have an EC2 instance ID on the session name, on the ARN there. So this is the IAM role attached to the underlying EC2 node. We've now run slightly at the top of the screen, run a patch command. We've added a role to that service account. So, and we display the service account here. Now you see which role we want to assign to the service account. And we deleted the previous pod. So now the next pod that gets created in this deployment that's using that service account, we'll look at the volumes and see which volumes it has. So before we just had one, that was the regular service account token, and now you can see we have two. So we have what we call a projected service account token, and the audience is set to STS. So this token is not intended to talk to the Kubernetes API server. This token is meant to be used with AWS. We list the secret directory. You can see there's a token in there. I dumped the token output, decoded it to see what's inside. You can see there's a service account name, so this is a token for that service account. When we shell into the pod now, this new pod that has this token, and we run get caller identity, we're not using the EC2 instance role anymore. We're using the IAM, the service account role. So that's a really fast, quick demo, but it kind of gives you an idea of how easy it is to just start using this. So want to close out with a little bit of a summary here. So there's a lot we talked about.
Yeah. So just before we finish, I wanted to share with you our security defense in-depth strategy at HSBC. So this is not all of it, but I've tried to capture the main bits. So some of this we talked about. So we covered items like utilization of Kubernetes pod security policies, pod security contexts, so to inject essentially rules using pod security policies, and to set your context to ensure that things are isolated from one another. We also utilize namespace, which we talked about earlier. So we talked about namespace for isolation in Kubernetes, service accounts for identification, and utilization of RBAC, so creating basically least privileged roles with permissions. So we've got cluster administrator roles, app developer roles, and then separation of roles all the way through. So think IAM for Kubernetes when you think about RBAC. So we also utilize things like IAM roles for pods, and well, I call them pods, but service accounts. So effectively there, we're utilizing that because we want least privileged models. So we've got AWS resources outside of the cluster. So DynamoDB, S3, whatever the resource is. And we want to ensure that the pods within our multi-tenanted clusters have least privileged access, where only a specific team can access its resources. So we utilize IAM roles for service accounts for that purpose. Kubernetes networking policies. So we spoke about that briefly earlier. So options around that in terms of using native Kubernetes policies or Calico, for example. We also utilize, with Kubernetes network policy stuff, we utilize ingress controller. And we're doing that combined with other networking controls to really control the cluster ingress and egress in a fine-grained way. So not all pods have ingress access, for example. By default, pods can't communicate with one another, so we don't allow east-west communication by default, because you shouldn't really the case in that scenario. And in addition, we control egress access in a fine-grained way. So only specific pods which are allowed to have egress access get egress access effectively. So image management we spoke about, we utilize all the policies that we gave the example of earlier and others. So we control in a highly controlled way the use of images to ensure that they're scanned and they don't have any vulnerabilities, and that a man-in-the-middle style attack can't happen on our CI/CD pipeline. We also enforce that people can't pull images into the cluster themselves or push images outside, utilizing the controls we spoke about. We also use the Linux-related security controls we spoke about, so things like SELinux, managed access control, where we've got the Linux security module we're utilizing for that, which is not an Amazon EKS product. It's a effectively an open source plugin, not even specific to Kubernetes, but can be used with Kubernetes, and we're doing so in that particular case, and people do use it for Kubernetes. And we have SecComp as well, as we mentioned, which filters out syscall rules. So there are many others that we utilize, and we use things like private endpoints, as mentioned earlier, and we utilize Amazon controls like VPC endpoint policies, restricting those, so only principals allowed can access essentially resources. So again, it's just to give you an overview, essentially, of what we do. As important as the overview of the controls themselves, which you can take away yourself and apply to your own clusters, the goal to us was equally important. So at HSBC, we adopted, essentially to combat all the risks we spoke about earlier and security attack vectors, a multi-layered approach where really our goal was to put as many barriers as we can in the form of security controls to prevent the possibility of container breakouts, isolate containers from one another, and effectively essentially protect the host resources and that of the resources of the containers and the pods. We also wanted to limit the surface attack area of basically a container breakout. So hardening of the host OS, so all the controls we spoke about just a minute ago. And also container runtime, which we didn't speak in intricate detail on, and also protecting of Kubernetes processes, and protecting basically of the pods and containers by injecting rules into them. We also wanted to limit the blast radius area, so that was both within the cluster and outside the cluster. So whilst we have controls all within the Kubernetes space, Linux, and AWS around the cluster itself, we also have controls outside of that that limit the blast radius, essentially. So to the point, we did all this, and it was important to us to do that to protect our customer data and our applications and essentially our clusters. But we did all this whilst trying to automate it all. So with SELinux, like for the example I showed you, it's possible to do all of these controls to automate through infrastructure as code or to automate through tooling. So at HSBC, it was very important we did that so that we had agility still for our developers and adaptability. So it's, again, not one size fits all, but we give the tools and the means to be able to implement security, so we protect our customers' data, we protect our applications, and we protect also our clusters, and thereby allowing to run highly secure workloads, essentially, on Amazon EKS. So that's really it, I think.
Yeah, so just some final recommendations we want to leave you with are leverage your Kubernetes security features. We talked about some here. There's more, but we encourage you to do that. Reduce attack surfaces. So in the beginning, we talked about threat modeling and what are the actors and capabilities that they have, and the different CIAA model and how you can think about securing your systems. Also, automate configuration and deployment. Like patching is critical. So above all, keep thinking in layers. Thank you all.
Yeah, thank you.
We won't be doing any Q&A, but you can catch us out in the hallway. Please fill out a survey. We really value your feedback and would love to hear from you. Thank you.
Thanks.